Good morning, good afternoon, good evening, depending on where you're joining us from. And thank you for joining our session on how we benchmarked 2 million requests per second with HAProxy on ARM processors. My name is Kailas Jawadekar, and I'm responsible for software ecosystem on top of ARM Neoverse architecture. I'll lead the first part of this presentation. I'll provide an introduction to ARM and the benefits of running your workloads on ARM Neoverse-based infrastructure, and then pass it to my co-presenter Nenad, who is a principal solutions architect at HAProxy. Nenad will talk about HAProxy's achievement of over 2 million forwarded RPS on AWS's ARM Neoverse-based Graviton 2 powered instances, as well as the associated DPBench project. So let's get started. So in this section, we'll talk about ARM and what it means for your business to run your applications on ARM-based infrastructure. But before we do that, let's take a step back and discuss what is ARM all about. Let's just do a quick overview of who we are and what we do. ARM is a very unique company with a very unique business model. We're the global leaders in the development of licensable compute technology. That is, we develop CPU IP and license it to our semiconductor partners, and our revenue is via licensing fees and royalties from these partners. As you can see in some of the stats highlighted over here, we have over 530 licensees, which include industry leaders such as AWS, Qualcomm, Marvell, etc. There are over 1910 licenses, and we're growing by 100 plus every single year. There are already over 190 billion ARM chips out there to date. And what's interesting about that is the significant growth we are experiencing over the past few years. As shown here, just in 2020 alone, 23 plus billion chips were shipped. An interesting anecdote is it took ARM 22 years to ship first 50 billion chips, and then it took us the next 4 years to ship the next 50 billion chips. So we are really experiencing a very exponential growth. And to support that growth, we are investing heavily in the server class IP that can drive infrastructure from edge to cloud. So it's a very unique ecosystem-led, partnership-friendly business model. We succeed when our partners succeed. So we work with our partners very closely, and our roadmap is driven very heavily by the requirements from our partners. Our partners can then leverage those innovations and build their platforms and solutions around our IP. So we are like R&D arm, no pun intended, for our partners. From ARM Infrastructure Group and ARM Neoverse platform perspective, where we are seeing a lot of traction and where we are focused on are these four main areas. From right to left, infrastructure and IoT edge. Historically, we have been very strong in the embedded devices, infrastructure, and IoT edge space. And we continue to see exponential growth in this space, especially due to the trillions of new devices that are coming online and will generate a ton of data at the edge. To ensure a consistent cloud-native experience at the edge, we recently defined Project Cassini. Project Cassini enables a standards-based approach to defining hardware and firmware requirements for secure cloud-native stack at the infrastructure edge. 5G and carrier infrastructure is another area that's driving a lot of growth for us. ARM's lower power requirements, high efficiency, and adherence to open standards make it the best architecture for deployment closer to the cell tower, for open RAN type of deployments, as well as the most efficient architecture for 5G core telco networks as well. High performance computing, or HPC. The best-in-class performance and compute density for ARM architecture has always made it an ideal candidate for HPC. Case in point being ARM-based Fugaku supercomputer has now been named the #1 supercomputer in the world for 3 years in a row. But where we are seeing the most traction over the last couple of years is with the cloud providers. As more and more enterprises move their workloads to the cloud, the question they're asking is, how can I get best price performance for these workloads? At the end of the day, these enterprises don't necessarily care about the compute architecture underneath, but they do care about their applications and workloads. And they want these workloads to be run in the most efficient manner on an architecture that gives them the best price performance. And that architecture happens to be ARM Neoverse-based architecture. Later in the presentation, we'll share some benchmarking data that shows ARM-based instances consistently outperforming comparable x86-based instances and at a lower cost as well. So let's talk about a real-world example of how ARM-based CPUs are being developed by our partners at AWS and leveraged by many of their customers to run their workloads. As you know, AWS Graviton 2 processors were introduced at AWS reInvent 2019. These are custom-designed CPUs developed by AWS and are based on 64-bit ARM Neoverse N1 cores using 7-nanometer silicon technology. In internal as well as third-party benchmarking, these have shown to offer up to 40% better price performance and 20% lower cost over comparable M5 x86-based instances. For Graviton 2, depending on your workload requirements, various instance types are available. These include M6G for general purpose workloads, C6G for compute intensive workloads, and R6G for memory intensive workloads. There are local NVMe SSD storage options available as well. These include M6GT, C6GT, and R6GT. Additionally, AWS offers bare metal instances ending with .metal as well. Multiple AWS services such as AWS Code Build, Code Commit, as well as ECS and EKS, and many more are already supported on Graviton 2 CPUs. Also, as we discussed, many of the enterprise workloads we talked about are already supported for running on top of Graviton 2, and the list of these supported workloads is growing every month. And there's an ever-increasing set of customers that are adopting Graviton 2 architecture to run their business-critical workloads as well. So we talked about how Graviton 2 M6G instances have 20% lower cost than x86-based M5 instances. But ARM instances are also much better performing when it comes to running some of the common business workloads. This slide highlights the performance uplifts we have observed per vCPU for various workloads running on Graviton 2 M6G instances versus running the same workloads on top of x86-based M5 instances. As you can see, for general purpose workloads, we observed 24% better performance for spec floating point benchmarks, as well as 44% better performance on spec integer benchmark, as highlighted over here. For EDS simulation on Cadence, we observed 54% better performance. For Memcached, which is a popular key value data store, we noticed 43% better performance. And for KeyDB, we observed a whopping 65% performance uplift, and so on and so forth. On the right over here, I have added links to some third-party results as well, so you don't just have to take our word for it. So that was a very quick introduction to ARM Neoverse-based instances on AWS Graviton 2, and the performance uplifts and cost benefits you can observe by moving your workloads to ARM-based infrastructure. We're obviously seeing similar benefits for HAProxy as well. And to talk all about that, let me pass it to Nenad, who will cover the benchmarking HAProxy team performed on ARM-based Graviton 2 instances and the incredible performance results that they observed. Nenad, over to you.
Thank you, Kailas. As Kailas already mentioned, my name is Nenad. I'm a principal solutions architect at HAProxy Technologies. And today, we're going to talk about how HAProxy achieved 2 million requests per second using ARM-based instances on AWS. We will also talk about how we have created a DPBench project, which enables us and many other people to benchmark data plane components. So let's start with how to benchmark. And here we will see that not all benchmarks were created equal. The problem with benchmarking low-level components like HAProxy that have to have extremely high performance is that you will run into several pitfalls when doing those benchmarks. We have observed and experienced ourselves several problems when benchmarking, and usually we divide those in 5 categories. So the first ones are the most obvious ones, which is configuration issues. So the configuration issues can be both operating system configuration or the component being benchmarked configuration. With HAProxy, we have evolved through the years from a single process to multi-process to multi-threading. Oftentimes these days, you will find many configurations on the internet still referencing old ways of doing things. So if you apply a single process configuration to a new version of HAProxy that is supposed to be running multi-threaded, you will get subpar performance. Same things apply to the operating system. Kernels evolve, there's many new ccTLs available, some are changed, so people just going in and copy-pasting things off the internet usually leads to worse performance than you would get out of the box with regular operating system tuning. So as we're benchmarking a proxy, we also need a traffic source and a traffic sink. So the traffic source is just a load generator. Usually when benchmarking, we use HTTP load generators. There's many ones on the market, but it is critical that this component does not introduce any additional latency or cause any other problems with the benchmark. Same applies with the traffic sink, which is just an HTTP server. So the HTTP server needs to be able to respond very fast. It is good if it's going to have configurable response sizes, so you can benchmark different response sizes, and depending on that, the network throughput. Other things we have observed are hardware issues. So when choosing a hardware to benchmark a component, you need to ensure that you have adequate CPU capacity, adequate amount of memory, and adequate amount of network throughput. As we will see here, HAProxy scales almost linearly with the number of cores to a point, but after that point, there's other things that need to be taken into consideration, which is how locking is performed, how thread synchronization works, and other challenges of multi-threaded programming. And the last part is network issues. So as we're benchmarking network components, it is good if all the components were connected to one switch. That will ensure that we don't take any unnecessary hops to the network and don't introduce latency into the benchmark that's not related to the benchmark itself. Here, you will see one graph that shows one of the benchmarks found on the internet. And it shows that HAProxy at 250 concurrent connections is passing less than 500 requests per second, which is for sure not accurate because probably the CPU on my mobile phone could do more. And usually when we see these benchmarks, we go, what? Makes no sense for these benchmarks to even exist. And this is exactly why DPBench was born. DPBench, short of Data Plane Bench, is a suite of benchmarking tools specifically designed for benchmarking data plane components like reverse proxies. It was created by engineers at HAProxy in collaboration with some of the engineers from Nginx. And even though these two technologies compete on the market, both of us want to ensure that benchmarks that are presented to the customers or to the users are accurate and repeatable. So DPBench is an open source project available on GitHub, and it's a set of tools, scripts, how-tos, configuration files that are kept to a very high standard. This means that you will usually find configuration of various software tools there that are written by the authors themselves. This ensures that when you download this configuration file, you're getting the best you can get. And by doing this, you can get the best results this software can give you. And here we come to something that's very critical in benchmarking HAProxy or any other data plane component, and this is latency. Even though 2 million requests per second is a throughput-based metric, we still need to account for how much latency we're introducing into the workflow. The reason for this is that in modern environments, in microservices environments, service meshes, any modern application, a one client request usually maps to many backend requests that pass through many HAProxies or other proxy components. So if you only look at 99 or 99.9 percentile latency, one client request can map to maybe 10 backend requests, each of which maps further, and you could easily have tens or even 100 times amplification in terms of one client request goes through 100 proxies. So if you look at 99th percentile, that means that 1 out of 100 requests would have worse latency, which means that for almost every single one of your clients on your website or web application, they will experience slowdowns, suboptimal experience, and this will in the end affect your business and revenue. This is why with HAProxy and with this benchmark, we're focusing on tail end latencies. And we define tail end latencies as 99.9995 percentile. This means that only a small fraction of requests are not taken into account. And when doing this, it is critical to understand what other components in the benchmark could affect your latency. And on this graph, you see one such case. So the graph here represents throughput and latency. You will see two latency spikes happening 60 seconds apart. Here, it's fairly easy to identify what is happening. It's a cron job. So to alleviate this problem, we have just stopped the cron daemon, and the benchmark could continue using just all the available CPU power and not having these latency spikes. You will also see that at the beginning of the run, we're ramping up. The reason for this is that a lot of software out there for benchmarking, but even proxies, try to use memory in an optimal way. So they don't allocate and deallocate memory every time. This means they keep a pool of memory available. But this pool has to be established. So in the beginning of the benchmark, there's a lot of allocations happening, sockets being created, a lot of stuff is happening internally that is not happening after the initial warm-up period. This is why it is important to run your tools and then define the start of your benchmark after all the tools have been warmed up. And this is not everything. So you can also have latency can be introduced by many other things like ARP resolutions or other jobs being ran or CPU migrations. There's a lot of reasons why those latency spikes could happen, and you need to account for them. Most things that we have observed in the field have been documented inside the DPBench project. So be sure to check it out, and I think you will learn a lot. And the question is, so why did we test on ARM-based CPUs on AWS using Graviton2 instances? So the Graviton2 CPU is a great CPU for HAProxy. The reason is that it has 64 cores on one chip with uniform memory access. This means that there's no traversal across NUMA nodes, and this means that all of your memory access latencies stay the same. It also features per core L2 cache and shared L3 cache. One of the most critical things that we have observed is that by utilizing LSE, which are ARM large system extensions, we have been able to replace some of the atomics with atomic instructions from the LSE set and gain a lot of performance this way. For the AWS test, we have chosen the C6GN 16x large instance, which is a 64-core ARM-based processor, and the critical thing there is that it features 100 gig networking. This is very important if you're going to benchmark throughput with larger response sizes. This is the setup that we used. We used 3 instances. Each was the same 16x large C6GN, and they were connected using AWS 100 gig networking. One instance was running as a traffic source, one was running HAProxy, and one was running an HTTP server or a traffic sink. The source was running H1 load. H1 load is a load generator for HTTP that's available as part of the DPBench project. And on the server side, we ran HTTP term, which is again a very simple HTTP server that has fully configurable response sizes and is very highly performant to be able to sustain this level of traffic. In the middle, we had HAProxy. We benchmarked both 2.3 and 2.4, but in this presentation, we're going to focus on the 2.4 results, just to keep the presentation shorter. On the picture, you can see how the CPUs were mapped to various functions inside each instance. So you have a reference reference load generator, which is bypassing HAProxy and going directly to the server. You have 2 to 47 CPU cores assigned to the client, and the rest are for the network hierarchy. For the proxy, you can also see that it's about 45 CPUs for HAProxy and almost all the rest for network hierarchies. And these are the results. So here you can see that we achieved 2.07 million requests per second. And you can see the latencies on the graph as well. And it's important to note that we used 1150 concurrent connections to achieve this. You will observe on the graph that we also have a ramp-up period that was explained earlier. The latency results are like this. So at 2.07 million requests per second, HAProxy and the whole stack only adds 1.2 milliseconds of latency at the 99.9999 percentile. So it's important to know that this is not just HAProxy. This is the fact that you have an additional component, you have additional network traffic. There's network latencies that are small, but at this rate are noticeable. There's various buffers on the way, both in the card, in the kernel, and in HAProxy. And there's double the requests because there's one request from client to HAProxy, and then there's another from HAProxy to the server. And this is great, but people often ask, and rightfully so, with the web today being HTTPS based, how does HAProxy handle HTTPS at these rates? And here's the results. The results show that we only dropped 0.07 million requests per second when using HTTPS. So it's important to show that the CPU is so effective at encrypting and decrypting. This is, of course, using symmetric encryption. We're not taking into account new connections, that we only dropped a very, very small number in terms of raw throughput. The latency itself is different than it was before, and it shows that we can add up to 5 milliseconds in extreme cases. So we're talking about the very tail end of latencies. The reason for this is just the internal handling of SSL, and to even measure where exactly this is spent would be very difficult or nearly impossible. And this is it. So thank you very much for your attention. Please let us know if you have any questions, and we'll try to provide the answers.
Well, that was quite the exciting talk to close out day one of HAProxyConf 2021, and certainly quite the impressive performance achievement detailed by Kailas and Nenad. And we have them both joining us here today for the live Q&A. Hello, gentlemen.
Hello.
Well,
great. So as a reminder to the audience, you can submit questions in the stream on HAProxyConf.com, and you can also submit them on Twitter using the hashtag HAProxyConf. Great. So we'll get right into these questions. The first one, this is for you, Kailas. So are ARM Neoverse chips available for servers in on-premise data centers or currently just for the cloud?
So we are leading with the cloud, but they're available for on-prem data centers as well. So we are working with our partners Ampere. So if you have Ampere Ultra, they are essentially ARM Neoverse based cores. And they also have server offerings with the likes of Gigabyte, for example. So you can always procure servers from Gigabyte that are based on Ampere Ultra. And yeah, you can absolutely use that. And we encourage you use those in your data centers as well. Obviously, as I said, we are leading with more of a cloud-first strategy. But yeah, these are available for data centers, and you can certainly use those Ampere Ultra-based servers in your data centers as well.
Great. And this question is also for you, Kailas. So during your talk, you had described some of the impressive benchmarks for the Graviton 2 processor. So along with performance, you also talked about lower energy consumption for a more green data center. So with sustainability being such a big topic these days, do you have any thoughts on what this sort of technology could mean for the future of energy consumption?
Yeah, no, that's a great question. And I know we have talked quite a bit about performance, but I guess one kind of important metric we do need to look at is performance per watt. And that's what we have been focusing on, very heavily. See, the tension between, technology as a solution to environmental problems versus something that exacerbates the problem has always been there. But we think that we can have a net positive contribution to sustainability. And to achieve that, performance per watt is really a key to that. And that's something that's really in ARM's DNA right from the beginning. ARM's energy efficient processor designs have been enabling products from sensors to smartphones to cloud servers and even to supercomputers. So we feel that as a provider of this foundational technology, we are uniquely placed to reduce the environmental impact of compute while maximizing its benefits. So we have been working very hard alongside our ecosystem to decarbonize compute, leveraging our expertise in low power processing to really maximize the performance per watt. So just to give you a very specific example, based on our internal testing using Spec in 2017 benchmarks, servers based on ARM Neoverse can perform up to 60% more work while generating up to 40% fewer CO2 emissions than servers using traditional processors. You can guess which ones those are. So basically, what that means is if deployed broadly, Neoverse could increase cloud capacity by 25% by about 2030 without increasing any energy consumption. So that's the key part of it. So if you believe that technology should play an integral part in solving climate issue, then ARM-based infrastructure should really be your preferred architecture to run your workloads on, in my opinion.
Sure, and it seems obvious it's probably something that's only going to get more attention as we move forward. So really important.
Absolutely.
Great. This next question is for Nenad. If someone wants to run HAProxy on an ARM processor, do they need to compile HAProxy specifically for that processor, or will it simply work?
Well, that depends on what specific compiler was used. So, as is described in the blog post, the GCC, I think 10.2 compiles it automatically to enable the usage of LSE. And with older GCC versions, you need to specify the architecture on the compile line. And but we, as HAProxy, provide our enterprise customers with enterprise packages that are ready for ARM. And there are Docker images on the official Docker Hub, which have been compiled with LSE, so you will be able to utilize the full power of the ARM processors.
Excellent. Thank you for that clarification. All right, this is another one for Kailas. Are M6G instances cheaper than M5 purely due to hardware costs or efficiency, or is there a preferential partnership with AWS?
So it's a custom architecture essentially. So the AWS Graviton 2 processors are their custom designed CPUs that are kind of homegrown, designed by AWS, that are based on 64-bit ARM Neoverse N1 cores and use 7 nanometer silicon technology. So these have been built from the ground up specifically to run cloud workloads at AWS at the lowest cost point possible and at the highest performance point possible. So it's really the benefit of a custom SoC being designed for cloud workloads. You're really seeing the benefits of that, and that's one of the primary reasons why those instances kind of cost low. And the great thing is AWS has been able to. The cost point to build these SoCs has been low, and they have been kind of passed some of those costs on to their customers as well. So it's great for anyone who wants to deploy their workloads on AWS. If they deploy it on Graviton 2, they naturally get that 40% price performance benefit on Graviton 2 versus running it on standard x86-based instances.
And perhaps related to this, how do flagship ARM chips benchmark against flagship Intel chips in an isolated test environment?
So we feel that we do really well, and I think that's something that I highlighted as a part of my presentation. I think it's slide 5. So we did a fair bit of benchmarking across all sorts of workloads, across general purpose compute, across media encoding with X.264 with machine learning, with even EDS simulation, and things such as QDB for database workloads, etc. So, and pretty much in most of those workloads, we have seen a significant price performance benefit versus x86. Now we understand that Intel will continue to come up with newer versions such as Sapphire Rapids and so on and so forth, Ice Lake Sapphire Rapids that will have performance benefits versus their previous generation CPUs. But we also continue to invest in our roadmap, and we are fairly confident that we'll continue to at least meet and in many cases outperform x86 performance, and do that at a lower cost. So from our perspective, it makes clear sense to run your workloads on top of ARM-based processors such as Graviton 2.
Sure, impressive. Okay, we have time for one more question. This one's for Nenad. Where can we go to get more information about the DPBench project?
So everything for DPBench is contained in its GitHub repository. So go on GitHub, look up DPBench, and there's documentation there. There's the whole framework is there, as well as about a lot of additional explanations that will help you understand why benchmarking such low-level components is critical, and why it's also at the same time pretty difficult.
Excellent. So that's all we have time for today. Gentlemen, Kailas, Nenad, thank you so much for the presentation, for taking part in the live Q&A, and for joining us in HAProxyConf 2021. So really appreciate the time, and I hope you enjoy the rest of the conference.
Thank you.
Thanks so much for having us.